Hi everybody, this is a revision video for the first topic in Year 1 of A-Level Chemistry, Atomic Structure and Isotopes. Well, the specification is pretty detailed in terms of the content and the stuff we need to know and we need to learn, and that's routinely and easily available for you at the course website. First of all, the atom itself. The atom consists obviously of a nucleus, which contains the subatomic particles, neutrons and protons. Most of the mass is contained within a nucleus, and of course this diagram, the old-fashioned Bohr diagram, is certainly not to scale. Of course, the nucleus is very, very tiny, and there's an awful lot of empty space between that and the electron shells. Now you can call them shells or you can call them energy levels. The electrons orbit nucleus in these energy levels. This is the most likely place to find an electron. They're not circular railway lines, and the atom, of course, is not flat, because you're not, and you're made of atoms. So be aware of that model, because it's not really what actually it looks like. It's just a decent guess. The properties of the subatomic particles is frequently asked of you, and these are in this table below here. The proton relative charge +1, relative mass +1, neutron relative charge 0, relative mass also +1, and the electron relative charge -1, so opposite to that of a proton, and the relative mass. Now, there are several answers for the relative mass of an electron. 1/2000 is perfectly acceptable. There's no need to go into any more detail than that. We represent any element by its symbol. Here is lithium, and we associate with it two numbers. The smaller number is always a whole number. This is the atomic number. Fundamentally, the number of protons. It is this number which identifies the element lithium. Only lithium has atomic number 3, and only atomic number 3 is referring to lithium. So that is a unique combination that you must get clear. The atomic number is the identifier of the element, in this case lithium, number 3. The bigger number, the number in this case 7, is the mass number. This is the number of protons plus neutrons in the atom of lithium that we are looking at. This number does vary. The number of neutrons is not fixed. The number of neutrons does vary, giving different masses. These, of course, are called isotopes. And of course, when we take an atom, we can either remove electrons from it or add electrons to it. We never gain or lose protons in a nucleus. All we have to concern ourselves with is the number of electrons. Negative ions have got more electrons than they have protons. Positive ions have got fewer electrons than protons. We can readily work out the numbers of subatomic particles by some simple maths. The number of protons is the atomic number Z. The number of neutrons is the mass number A minus the atomic number Z. The number of electrons is equal to the atomic number minus the charge. And of course, if this is a negative value for a negative electron, then Z minus charge makes a more positive number. Well, of course, the properties of isotopes will all be chemically identical, because all isotopes of the same element have the same number and arrangement of electrons, so their chemical properties will be the same. Here are the three isotopes of the element carbon. Notice they are all atomic number 6. 6 protons equals carbon. The mass numbers are whole numbers, 12, 13 and 14, because as you can see from the table, there are different numbers of neutrons, not protons or electrons. In neutral atoms, numbers of protons are equal to numbers of electrons. And as you can see, the only difference between these isotopes of carbon, their mass numbers, is due to the number of nuclear neutrons. Well, the discovery and development of models of atomic thinking, of course, is an interesting one. Various people have contributed different aspects to it. Famously, J.J. Thomson had an idea that we had negative electrons embedded in a positive pudding, the so-called plum pudding model. The ideas, of course, changed and developed from a number of experiments. For example, the Rutherford experiment, which fired alpha particles at a thin film of gold leaf, and to their surprise, when the alpha particle with a mass of 4 was bounced right back from their foil, then of course that surprised them because it meant that the nucleus was a dense, positive and compact entity at the center of the atom. So that model had to change. The Rutherford model was better, and Niels Bohr came up with the idea that you're familiar with, the idea of a nucleus at the center with orbiting electrons around it. Well, that model is also slightly wrong, of course. It isn't two-dimensional. The electrons don't move around on circular tracks. The nucleus, yes, it's tiny and it's massive and it's at the center of the atom. The electrons are way, way away from that. And the idea now is that we have a three-dimensional model. The modern view of a model of an atom is one that refers to electrons as more likely to be located in orbiting clouds. The model changes. Well, some key definitions that we do get asked are the definitions involving the word relative. Relative atomic mass, relative isotopic mass. Every time you see the word relative, it means you must refer to our standard atom, carbon-12. We set the mass of carbon-12 to be exactly 12.000 and measure everything else against that standard. And by definition, the relative atomic mass, this definition is worth 2 marks, is the average or weighted mean mass of an atom of an element compared to 1/12 of an atom of carbon-12. And of course, 1/12 of 12 is 1/12 of 12 is 1. So the idea, whenever you come across relative, means you must mention carbon-12 in your answer. So here is a display which shows the 2 isotopes of a particular element. You can see their mass over charge, or very simply mass divided by 1, because these are regarded as having a 1+ charge, shows 2 isotopes with a mass of 35 and a mass of 37, with 2 different abundance figures. The percentage abundance up the y-axis, 75% is isotope 35 and 25% isotope 37. So in other words, in every 100 atoms of this particular element, which happens to be chlorine, 75 of them have a mass of 35 and 25 of them have a mass of 37. As I said, the m/z value is just a quotation on the axis there, which essentially is mass divided by charge. Since most of these particular ions have a charge of +1, then this is just mass over 1. The abundance details up the side and the accurate masses are all determined by mass spectrometry. This is quite a sophisticated instrument which measures those particular things by taking a sample of atoms, ionizing them, that is, knocking electrons off them, turning them into positive ions. They're then accelerated and collected. and counted. And so it's a very simple idea, but what it does is it sorts our isotope atoms into different masses, and it counts their relative abundances, as you can see. The percentage figures are easily turned into a relative atomic mass calculation, and we can do this on the next slide, and you'll see this is quite straightforward. We simply take the relative atomic mass is equal to the isotope abundance times the isotope mass, plus we add the second isotope times its abundance. So in other words, it's the sum of isotope mass times abundance. So in the case of our example here, it would be 35 times 75 plus 37 times 25, all divided by 100, and that will give us a calculated answer of 35.5. So the relative atomic mass of chlorine is 35.5 because it's a weighted mean. It's an average. It's not just simply 35 plus 37 divided by 2, because both the isotopes are not equally abundant. The 35 isotope, of course, is 3 times more abundant than the 37 isotope. So we do a weighted mean, as you can see here. And this, of course, as I said, was chlorine. Here is another example. This is a different element, and as you can see, we've got isotope masses of 70, 72, 73, 74, 75, not 71. And as you can see, there are different abundances. And on Earth, the abundance of isotopes does vary. In other places in the universe, we don't get different isotopes, but we do get different abundance figures on different astronomical phenomena, such as asteroids and other planets, probably. But we still calculate the relative atomic mass in exactly the same way. We've just got 5 isotopes to work with this time. So when we do our calculation, and this method you must know, to calculate relative atomic mass, we multiply the isotope mass, 70, by its abundance, 20.5. We then do the same for all the other isotopes, as you can see, and add them all up. So it's the sum of the isotope masses times abundances, all added together, and then divide by 100, because of course these are percentage figures. The answer we come up with in this case to 1 decimal place is 72.6. This is the element germanium, an element in group 4. Notice the relative atomic mass value is always quoted to 1 decimal place, and that is always the case on your periodic table. Yes, the relative mass numbers are always bigger than the atomic numbers, and they're also to 1 decimal place, whereas atomic numbers are not, they're whole numbers.